get started in about 5 minutes. We're waiting just one dignitary. We'll get started. Yeah, well, actually, you're more you're stepping in.
Okay, yeah. So,
Here, so you know, you arrived there? We'll get started. Let's get started. Good morning and welcome to the Fall 2023 renewal of the Biomedical Engineering Senior Design Expo and Competition. We acknowledge and appreciate the presence of our families, friends, well-wishers, faculty, dignitaries, and most especially the students who will be presenting today. I'd also like to extend a welcome to those who are joining us remotely on Zoom or on Facebook Live. We appreciate your presence as well. My name is Michael Christie. I'm the primary instructor for this course, associate teaching professor in the department, and faculty fellow of the Honors College. And I'll be moderating your program today. At this moment, I'd like to invite the undergraduate program director, Dr. Wei Chang Lin, to the stage to give some words of welcome on behalf of the department. Dr. Lin.
thank you, Dr. Christie, and good morning, everyone. Welcome to this special event. I see some excitement in the audience, which is great, and I saw some of the projects already, and so, you know, I must say, you guys have done a wonderful job and over the semester, and your projects definitely show your creativity and your knowledge about biomedical engineering, as well as your ability to work with your teammates, and I think that's really important. I want to thank the sponsors, for providing our students the opportunity to work on those realistic projects, and so really that enhances the educational aspect of the biomedical engineering program. And also I want to thank the advisors, faculty advisors, for their contribution to the project. And I think without their guidance, I think many of the projects probably won't be realized or get to the stage it is now. And finally, I want to thank judges for coming and your contribution to the event, and really enhance the experience of the senior design project. And we look forward to your feedback and to all the projects. Okay, so one final word, and thank you everyone for coming. And I think for senior design teams, you should be proud, and because you are showing your work, and there's no better moment than this. And we look forward to your exciting presentations, and may the best team win this competition.
Thank you, Dr. Lin. The Senior Design Showcase and Competition is a culmination of a year-long study. We're in the first semester under the direction of Professor Sharistan, who's right over there. Let's give it up to Professor Sharistan. Students are taught the rudiments of medical device product design, development, manufacturing, and project planning. In addition, students form teams and engage the medical device industry as well as clinics to secure projects and sponsorship. The first semester, Senior 1, ends with a proposal that has to be defended in front of a panel of faculty members. Yes? And the successful teams move on to Senior 2. In Senior 2, students work to finalize your designs, which is what you will see today, and manufacture working prototypes. They attend weekly lectures on design thinking, modern product and process development, advanced manufacturing, and quality assurance, as well as career development. Today I'm pleased to announce that the Senior Design Project program is healthy and continues to grow. In fact, this semester, the average sponsorship is about north of $1,900 per project, which is above our average, so we continue to grow in that area. We continue to hold steady with the number of projects. A annualized basis is anywhere from 20 to 22 projects per semester, and we are 100% sponsored by industry or the clinics. I think insert applause right there. Of course, none of this would be possible without the hard work of our students and the generosity and vision of our sponsors. Dr. Lin alluded to that, as well as the guidance of faculty mentors. Let's give them all a round of applause. Now for the competition. But first, let me introduce our judges. To my right and to your left is Ms. Melissa Benedicto. She's a researcher, graduate student, and in the history of this competition, only the third graduate student to serve in that capacity. Melissa! And Melissa was the inaugural winner of the Standard of Leadership Award, which goes to the best project manager. So she's here, she's going to be paying very close attention. Next to Melissa is Mr. Anthony Higgins from ERG Dynamic Biosolutions. He's a manufacturing engineer there. Let's give it up for Mr. Higgins. Next to Mr. Higgins is Ms. Lorraine Sierra. She's a regulatory affairs specialist at Skeletal Dynamics, and she's here to lend her expertise as well. Let's give it up. And our fourth judge, Mr. Alexander Capo, who's joining us remotely. He's a principal test engineer from Prometheus Therapeutics. He will be sending in his questions and also will be participating in the deliberations at the end of the presentation. Let's give it up for Mr. Capo. Rules of the competition. Each team will be given 10 to 12 minutes to make their presentations. There will be, at the 11th minute, the teams will hear and at the 12th minute, two things. And at that point, the teams will have 30 seconds to finish up their presentations. The Q&A will follow immediately after. Then we'll have a changeover, and the next team will take the stage. A little bit of housekeeping about today. At the end of presentations, judges will retire to EC 2680, the VME conference room, for deliberations. And lunch will be served there as well. There'll be refreshments there as well. And I'd like to ask all of you to join us about noon in the Panther Pit for lunch. So let's get started. Allow me to introduce team number one. Team number one, please come to the stage. Hexaflow, bone marrow aspiration needle. Team members, Samuel Eljuk, Amanda Sanchez, George Gonzalez, Jalaika Hamarillo, Laura Angulo. The project is sponsored by Surgentech. The faculty mentor is Dr. Shulang Zhao, and the alumni mentor is Mr. Ernesto Sanfiel. Let's give it up for team number one. Team number one.
Welcome, everyone.
Welcome, everyone. Thank you so much for joining us today. I'm excited to introduce a groundbreaking innovation that has the potential to reshape the landscape of bone marrow aspiration. The Hexaflow. We are Team 1.
My name is Samuel Hodge.
My name is Laura Angulo.
My name is George Gonzalez.
My name is Amanda Sanchez.
And my name is Jalaika Jaramillo. What is bone marrow aspiration, you may ask? It is an intrusive procedure designed to collect fluid bone marrow for diagnostics and the collection of valuable mesenchymal stem cells. However, as with any medical procedure, challenges arise. During cortical bone penetration, bone spicules are created, interfering with a density-graded separation, resulting to less aspirin concentration. This in turn affects the accuracy of diagnosis and the yield of stem cells. Despite these challenges, bone marrow aspirate holds an immense potential in regenerative medicine, which is our project's focus, and is integral in procedures such as spinal fusion and bone marrow transplant. Focusing on spinal fusion, mesenchymal stem cells are pivotal in the procedure's effectiveness, providing trophic support, stimulating tissue growth, and adjusting inflammation levels. Looking at the demographics of spinal fusion, on average, the patients are around 54 years old, and over 60, the occurrence of spondylolisthesis, a disease that is the benefits from spinal fusion is extremely high. What the medical industry needs is bone marrow aspirate with high stem cell counts, devoid of spicules, and a reliable and an effective method to obtain it. The current modalities in the market do not prevent bone spicules from being aspirated, and they need a filtration system. This adds processing time and yields less stem cells. The filtration system on average is around $700 to $1,000 on top of the initial costs. Like the pure BMC kit, a high-end filtration system still results to a 22.5% stem cell loss, which is a significant number that could result to worse patient outcomes. Now, I'm passing the floor to my teammate Amanda for the business needs.
Thank you, Jalaika. The bone marrow concentrate market is always rising and expanding. Due to its projected growth, there are plenty of big-name competitors involved already. Annually, 700,000 procedures are performed in just the United States alone. A procedure can cost anywhere from $1,200 to almost $6,000. When a procedure fails, or more specifically when a spinal fusion fails, due to a lack of concentration of stem cells in the bone graft, failed fusion syndrome results, and bone marrow aspiration is repeated, resulting in monetary loss. The smaller subdivision of the aspirate market is spinal fusion. Hundreds of thousands of procedures are performed annually. A procedure can cost upwards of thousands of dollars. And yet the failure rate remains at 20%, resulting in a potential monetary loss of $3 billion. A wide variety of patients can benefit from a successful spinal fusion. For instance, the total number of patients suffering from conditions treated by the procedure make up a large portion of the global population, at 1.2 to 1.6 billion individuals. Despite the prevalence of conditions treated and aided with bone marrow harvest, conventional bone marrow filters are unavailable in some countries due to regulatory constraints. Yet, faulty bone marrow aspiration can lead to failed fusion syndrome, which can incur intractable pain and a disruption to the daily lives of patients. So, how can we address this issue on a global scale? First of all, we need to focus on obtaining a high concentration of stem cells in bone marrow aspirate. Plus, bone marrow aspiration is a timely matter due to live cells being involved. So it is critical to develop a more sustainable and reliable method of filtering invasive bone spicules from aspirate. Now my teammate George will discuss our solution to this.
Thank you, Amanda. Our team's proposed solution is to design and manufacture a bone marrow aspiration needle that is capable of preventing the aspiration of these bone spicules in the first place, allowing us to bypass the need for additional bone marrow filters to obtain an aspirate that is ready for centrifugation and concentration. Here we see our market requirements and design inputs, with the most important of which being the first one, where the team must manufacture the needle's inlets to be 300 microns or smaller in diameter to prevent the aspiration of bone spicules. Other important design inputs include those for cell viability and needle strength. Here we see our remaining market requirements and design inputs that feature things such as interface compatibility, biocompatibility, and sterilization. Moving on to our design concepts, here we have our first two, the mesh filter bone marrow aspiration needle and the 100-hole bone marrow aspiration needle. Both have similar pros, being capable of preventing the aspiration of bone spicules. However, both have a similar con, not being very cost efficient to manufacture. So finally, here's our MVP, the Hexaflow bone marrow aspiration needle that features several advantages. First of all, it has more inlet surface area than our other two design concepts, allowing for it to induce less shear stress on the bone marrow as it flows through the inlets. Secondly, it is more cost efficient to manufacture, as it features a more simplified design. Finally, even with all this, it still manages to have inlets small enough to prevent the aspiration of bone spicules with a slot width of 290 microns. Here's a video demonstration of how our device will be used and how bone marrow will flow through the inlets. So, through the literature, the team found that bone spicules typically range from 200 to 1,000 microns in diameter, with spicules of 500 microns or less being very rare to find. So this begs the question, why not simply make the inlets 200 microns or smaller in diameter to completely prevent the aspiration of bone spicules? This is due to the fact that the manufacturer that the team chose to create the inlets, Trontec, is only capable of making cuts as small as 254 microns. So the team decided to move forwards with 290 microns as the slot width as an appropriate balance between these two numbers. The team also decided to incorporate 6 slotted inlets to increase the overall inlet surface area of the needle. To determine our MVP, the team also decided to run computerized simulations on our top 2 design concepts, the Hexaflow bone marrow aspiration needle and the 100-hole bone marrow aspiration needle, which was our second design concept. And the Hexaflow was, of course, our MVP. Here we see a computerized simulation that simulates 500 newtons of compression onto both design concepts. Here we see the results for stress that show that both needles never reached their yield strength, so they passed for this test. The results for this displacement that show that overall displacement was very minimal, and the results for strain. Overall, the results of this simulation show that both needles are capable of meeting the requirements for the simulation. So the team also decided to conduct a fluid dynamic simulation with a velocity profile of bone marrow flowing through the inlets of each design concept was obtained. Using this velocity profile, the inlet velocity of the bone marrow was obtained and used to calculate the shear stress induced on the bone marrow by both design concepts. What this revealed to us overall was that the Hexaflow bone marrow aspiration needle induces less than half of the shear stress on the bone marrow as it flows through the inlets when compared to the 100-hole bone marrow aspiration needle. So, due to this, the team decided to move forward with the Hexaflow bone marrow aspiration needle as its MVP, as well as the fact that it is more cost efficient to manufacture. So, following me will be my teammate Laura, who will discuss the prototype materials.
Thank you, George. Our prototype uses 316 stainless steel, which is a common metal used in medical devices, as well as ABS plastic, which is a thermoplastic polymer. As you can see in this video, the components of our needle are the lure lock, which allows for the connection of a syringe. We also have the trocar taper tip, which allows for puncturing through tissue, and most importantly, the bone. We have the 6 slots, which are paramount for our design because they filter out the bone spicules that we don't want in our sample, as well as a cannula that allows for the passage of the fluid bone marrow, and the stylet, which adds firmness to that cannula. In the process of manufacturing our design, our team faced some external constraints, which led us to brazing the needle tip onto the cannula. And after this, we machined the slots using Sinker EDM, which utilizes electrical discharge to cut the material. Here, to verify our design, we tested for microparticle aspiration, for cell viability, for needle compression, for the lure lock, and the weight of our needle, and they all passed, as you can see. However, the bone block test was determined to be future work due to the manufacturing constraints we faced. Now, we would like to share with you some of the most relevant test results. For the microparticle aspiration percentage test, we measured the percentage of spicules aspirated by competitor needles, some of which Jalika mentioned earlier, as well as our very own needle, and we tested the Alara needle, the Rampack needle, the BB needle, and they all gave us a percentage of about 13% spicules aspirated. On the other hand, we have our very own design, which aspirated 0% of the spicules. For the cell viability test, we also found great results. With the help of a PhD candidate, we were able to perform cell counts before and after stem cells were aspirated through our prototype, and we found 100% cell viability. For the needle compression test, we were able to measure up to 580 newtons of load, and which surpasses our design input of 500 newtons. Now, Samuel will take over with the project cost.
Thank you, Laura. The total cost for our project was $4,622 with 11 cents. And the total cost for our product was $1,340 with 45 cents. Our medical device is classified as a Class 2 by the FDA, and the regulatory path is the 510K. And these here are the applicable standards for our device, and the one which we use the most was the ISO 80369 because it's the one that's used for our lure lock. Our most important future work is the bone penetration verification test, which we couldn't do because we had manufacturing issues, and to increase the sample size for our other verification tests. Our medical device offers patent opportunities because currently on the market, there are no other bone marrow aspiration needles which incorporate an innovative filtration mechanism. And our biggest accomplishment for this project were to develop a particle aspiration rate test, communicate with local machine shops to manufacture our device, and to perform multiple verification tests on our device to make sure it works and to prove that there's potential to solve our clinical need. And finally, a big thank you to everybody who helped us, our references, and thank you very much. We are open to any questions.
Thank you, Team 1. Thank you, Team 1. Thank you, Team 1. Judges?
Great presentation, guys. I have a quick question. So I know you didn't get around to do the penetration testing, but what are different ways that you think you can make sure that when you're pushing the needle down into, there's no like blood clotting, or you won't be introducing additional reasons for it, like the surrounding bodies have issues? Like how can you tell your customers like, oh, this is actually going to work and we're not going to have any clotting inside of the kind of opening that you have at the end of the needle?
Yeah, so typically with bone marrow aspiration needles, a common practice is to wash it with heparin, flow heparin through it, as well as in the syringe, have a little bit of heparin in there so that the bone marrow itself doesn't clot. So with that mechanism, that's been proven to be an effective way to prevent the bone marrow from clotting, as well as anything inside of the patient.
Okay, so great presentation, by the way. Also, when you guys showed that one slide about you said 500 newtons of force, where's that force coming from? Is that the force required to push the needle through, or?
So we found in a research article that the maximum force that was actually found required to penetrate through the bone when during bone marrow aspiration, the pelvic bone, they found it to be 250 newtons, and we decided to do 2 times that as a safety factor.
Just be safe, okay. Then the one simulation showed that it kind of failed. Well, this device kind of failed on one side. So how do we explain that to a patient?
Oh, you mean the one where it looked like it was a little bit deformed?
Yeah.
Yeah, so.
Guys, go back to the
Yeah.
picture.
Yeah, so we were also a bit concerned with how that looked, but then upon inspecting, upon inspecting the values for displacement, we saw that it was actually in the range of microns. So due to that, we weren't concerned moving forward with the design. As well, we also did our compression test, and we didn't find any deformation in the design.
Yes, to add to that, this picture is a bit exaggerated, but as he mentioned earlier, the numbers don't lie. Sandra was a bit dramatic on that. But the numbers are within the specific range that we wanted. Yes.
Overall, great presentation. I was going to have the same question regarding this hearing. So thank you very much.
Okay. Thank you, Team 1. Oh, yeah.
Okay, yeah.
Yeah. Oh, I was like looking for my iPad, sorry. No, we're just
I now call team number 2 to the stage. Team number 2.
Thank you.
Dysphagia screening tool for oropharyngeal dysphagia. The team members, Robert Rodriguez, the project manager, Herman Suarez, Sophie Hawks, Andrea Lopez, and Alyssa Wera. The faculty mentor is Dr. Wei Chang Lim, and the alumni mentor is Mr. Omar Lopez. And this project has been sponsored by Sigma Biomedical. Let's give it up for team number 2.
Good morning, we are group Fall 2, and our senior design project is on the dysphagia screening tool. My name is Andrea, and my teammates are Sophia, Herman, Alyssa, and Robert. So to start off, dysphagia or difficulty swallowing is a condition that millions of Americans deal with every single year. Oropharyngeal dysphagia, or OD in particular, is prevalent in many neurological conditions. Our proposed solution is to create a non-invasive screening device that can be worn in the neck area and can be used to accurately screen for oropharyngeal dysphagia using swallowing signals. So OD is prevalent in around 13% of the geriatric population, those aged 65 and older, and more than 60% of those in institutions such as nursing homes are affected by OD, of which the most common cause is neurodegenerative diseases. So as you can see, the most common causes of OD is progressive chronic disease, neuromuscular disease, and structural causes. The estimated cost for patients who are in the hospital due to complications of dysphagia is around $7,000 US. In the average, in the U.S. medical care system, on average, annually, the estimated cost is around $4 to $7 billion. In the United States, up to 15 million Americans have reported difficulty swallowing, and according to the U.S. Department of Health, at least 70% of those who reach the age of 65 and older will need long-term care in their life, whether it's living in a nursing home or having assisted living. And unfortunately, over 60,000 Americans die every single year from complications of dysphagia, of which the most severe complication is aspiration pneumonia. The global dysphagia market is set at $3.1 billion and is estimated to grow to $4.6 billion by 2029. The North America market accounts for 36% of the shares, and it has an annual growth rate of 5.3%. From the long-term care statistics in 2022, there are around 65,000 nursing homes and long-term care institutions all throughout the U.S., and our goal is to have our device accessible to those long-term care institutions. The scope of this project is to design a product that will be able to detect swallowing signals and hopefully act as a future screening device when it comes to characterizing the abnormal swallowing signals that have to do with dysphagia. And for our device, it is crucial to understand how the swallowing mechanism and anatomy works, which Sophia will now further elaborate on.
Thank you, Andrea. So the anatomy of the pharynx, also known as the throat, is composed of 3 boundaries. You have the nasopharynx, the oropharynx, and the hypopharynx. So our screening device is going to be focusing on the hypopharynx boundary because this is where the high bone will play a crucial role in detecting swallowing vibrations. The physiology of deglutition, also known as the swallowing mechanism, is composed of multiple phases. You have the oral preparatory phase, the oral transit phase, the pharyngeal phase, and the esophageal phase. The most critical stage is found in the pharyngeal phase, which is a critical stage of swallowing as it is involuntary. And in addition to this, the epiglottitis changes the air channel to a food channel of the throat. In addition to this, the hyoid bone is raised by suprahyoid muscles and lowered by infrahyoid muscles, which produces the vibrating that we need for our screening device. So the detection points here is that we decided that the cricoid cartilage is the best choice for our screening device. This is because in multiple studies that we've seen, there is a good signal to noise ratio for our device in this location. The cricoid cartilage is found under the laryngeal prominence or the Adam's apple. So these are the market requirements and design inputs that we have for our screening device. We decided that the appropriate placement of our screening device is considered an important market requirement, as the sensor should not be displaced more than 1.2 millimeters. In addition to that, we decided that the adhesive tape that is attached to the screening device should not tear easily, as this will affect the placement of the device and cause patient discomfort. We also have market requirements and design inputs related to the data acquisition, which is going to be covered later on throughout our presentation. It is also important to consider the current modalities that is used to treat oropharyngeal dysphagia, which Herman is now going to talk about.
Thank you, Sophia. So, some current modalities that are used nowadays to diagnose OD are video fluoroscopy, endoscopy, and FEES. Some common cons that all of these have is that they're highly invasive, expensive, and uncomfortable to the patient. So our project tends to tackle this by being a simple, non-invasive screening device. So these are some of the design concepts that we came up with. So the first one is like a necklace to be worn around the patient's neck, and where the accelerometer is inserted into that small chip there in order to record the signal. And in the second one, the 3 rods would be taped to the patient's neck, and the accelerometer would go into that slot, having direct skin contact with the patient. And then these 2 were not chosen simply for, since our accelerometer is very high sensitivity, it would cause a lot of noise to be added to our signal. And then lastly, our MVP, or the concept that we move forward with, is like a block which has a curved surface in order to fit the anatomy of the patient, and the accelerometer slides into that box and is sealed off in order to record the signal. So these are 2 simulations that we ran. The first was to simulate the motion of the patient's Adam apple, and the second is to simulate the load that will be placed on our housing, which is basically just the accelerometer. In order to manufacture our product, we first designed the file on CAD, which was then sent to a lab here at FIU in order to be 3D printed. Then, after some soldering that we had to perform on the accelerometer, we had to make some minor adjustments using a Dremel, which was then accounted for in the final CAD file. So a simple system overview, as you can see here. So the accelerometer is inserted into this housing, which is then sealed off by this block here, and it's taped onto the patient's neck, which is then ran through to this MyDAC board, and that is connected to the computer in order for signal processing. So in order to process our signal, we recorded in 2 domains, the time domain and the frequency domain. And this accelerometer that we use specifically is a triaxial, but since we're only concerned with the z-axis and the y-axis, and then this signal was then amplified 10 times in order to get a clear reading as seen here. This was then converted to the frequency domain using a fast Fourier transform, or an FFT analysis, and that was then bandpass filtered from 0.1 hertz to 3.5 kilohertz. We performed verification tests on all 8 of our design inputs, of which our device passed, and Alyssa will now elaborate on.
Thank you, Herman. So verification tests play a critical role in ensuring the reliability, safety, and efficacy of our device. These tests are designed in order to make sure our device meets its performance and functioning needs. So as seen here, we have a total of 8 verification tests, and the most important thing to note is that all 8 were passed, and through these we were able to rectify any potential problems. So over the next 2 slides, I'll elaborate a bit more on 2 of our protocols. So for protocol number 2, detailing how the device must be able to detect vibration during swallowing, we emitted signals at known frequencies, both within and outside of our filtering range, that were programmed into our bandpass filter. So as seen here, signals that were seen on our FFT that were within our filtering range were recorded as a spike. So in this instance, there is a spike at the 2500 hertz range. Any signals that were outside of our filtering range were not recorded on our FFT, and as seen in the table, all of our chosen frequencies were deemed as passed, and this protocol was successful. Now moving on to protocol number 4, which details the strength of the tape's adhesiveness. Due to the skin being a low surface energy substance with a surface tension between 25 to 29 UINE per centimeter, we concluded that our tape chosen must have a lower or equivalent surface tension in order to ensure both patient comfortability and device reliability. So as seen in the table, and graph. All of our findings meet these needs, and this protocol was also successful. Now for our cost analysis, manufactured at a larger scale of 100 units, our device would cost approximately $536.96. And for our regulatory assessment, our device is considered an FDA Class II medical device, and a 510(k) pathway is also recommended. Now moving on to Robert, who will discuss our engineering standards and close out our presentation.
Thank you, Alyssa. So in relation to our project, there's a few engineering standards that from our literature review and with our market analysis, we know that these standards are relevant to our project and will need to be able to get passed in order to receive FDA approval. There are a few standards I would like to point out. The first is ISO 10993. For our patient contacting materials, in this case our adhesive, we actually source an off-the-shelf tape that is already in compliance with this standard. So in our current design, we are already in compliance with this ISO 10993. Additionally, for IEC 60601, we know that for our product to gain FDA approval, we need to receive electrical safety testing. We haven't performed this test yet, however, in our post-market and further instructions with our sponsor, we have informed them that this testing is critical to move forward in this project. Moving on, we know that dysphagia already affects a large percentage of the world's population, and one of the problems with dysphagia is that it goes undiagnosed for a long period of time. So this is one of the problems that we have tackled and hope to address with our design concepts. Additionally, our low-cost manufacturing process will make this product readily available not only to the domestic markets, but to the international markets as well, increasing overall global awareness. Additionally, our portable solution is able to be used by a wide range of healthcare professionals and doesn't require specialized physicians such as in our other solutions currently on the market. For patents and opportunities, based on our market analysis and a review of products that are currently on the market, there are no current products that offer dysphagia screening non-invasively. This will allow us to have a very viable patent opportunity moving forward. Additionally, we want to do clinical trials on a wide range of demographics to prove that our device works on a wide range of people. We also want to add a wireless functionality to increase the overall patient comfort and marketability of our product. We would also like to incorporate some machine learning strategies to improve the overall screening efficiency and accuracy of our product over time. For the all intellectual property in relation to this project and with our product, it all belongs to our sponsor, Sigma Biomedical. We would like to acknowledge our sponsors, our professors, our administrator, our advisor, and our alumni mentors. Thank you. And these are a few references in relation to our presentation here today. I hope you guys all enjoyed our presentation and are open to any more questions.
Thank you. Questions for team number 2? Comments? Questions?
Good presentation. So I have a quick question. Why specifically did you go for tape? Because if you have tape like on your neck or something, what happens if a patient is allergic to that specific tape? Is there another alternative you can think of? Like also, for example, the machine kind of fell off the tape. The tape was no longer adhesive. So what would happen if it's not adhesive during, like if your reading is going and then all of a sudden it just falls off?
Well, I feel like, So I feel like the reason it might have fallen off this is because it's not really skin, it's kind of like a silicone model, but we've tested and we've actually stuck the tape, on skin, actual skin, and it has not fallen off during our testing. Our tape is from 3M and it's already pre-made, and included in our standards is this tape was actually tested on animals already, and we know for people who may be allergic to anything or have problems of that kind of sort, that this tape is able, there's no latex, there's no anything, it's a silicone, and there's a silicone half of the tape, and that's meant for the skin, and there's an acrylic side of the tape, and that's meant for the device. So this tape was pretty much already manufactured in the most optimal for both adhesion to the device and the skin. But if we wanted to include like non-adhesive,
Yeah, and our design concepts, which Herman actually already elaborated on, and there are designs that involve a non-tape adhesiveness, for example, like a mechanical fixture. We noticed that in our simulations, it would introduce too much noise when a person was swallowing, because it would be attached to more of other areas of the neck and not just our detection points. That's one of the reasons why we decided to go with only a tape adhesion.
Okay, protocol. So, what did you prove your concept? And what did you prove it on?
So our protocols, we divided it into first protocols for the actual fixture device to make sure it wasn't going to move throughout the test. And we did protocols on the actual adhesiveness of the test. We also did for example, a drop test to make sure it wasn't moving based off of our first DI, that it wasn't moving in either of our axes. As I can go back to that first DI and kind of explain to you how we did that one. Yeah, so for our first DI, we actually did a drop test in either of those directions with that adhesive on a cylinder representing the throat, which would be our adhesion points, and there was no movement either direction for that as well. We also did protocols in relation to the actual signal that we were receiving to make sure that we were receiving the actual signal that we wanted and it was being processed. So it was the bandpass filtering. We also did additional verifications, for example, the sensitivity accelerometer. So we tested forces from 0 to 2 Gs on the accelerometer and proving that the forces that we were emitting on our system were actually the ones that we were receiving. And we actually passed this protocol as well.
Okay, so usually in the worst case scenario business. So, worst case scenario, piggyback on her question, why go with the adhesive? Because, not everyone is gonna be dry in the doctor's office. Some people are nervous, some people are sweating. So how do you combat that with the adhesive instead of going with the device that wraps around, the neck?
So we actually have a placement protocol in for our device so that when a physician or any healthcare professional is going to use their device, we actually have instructions for the actual sanitization of the skin, for example, with an alcohol wipe. So that's one of the problems that we've thought about and actually addressed, that we actually have in our package for our sponsor, so that, for example, when the proper placement of the device, we know that's something very critical, that you can't just take it out and put it directly onto the skin. So we actually have steps in place. For example, make sure wipe the area with alcohol wipes, along with sanitization process of the actual device itself, to ensure that it sticks cleanly onto the skin. You don't want to stick it onto a dirty skin or anything of that sort.
You're not gonna do that, but the person's gonna sweat. So the
Correct.
sweat, the glands are under the adhesive or the tape. So
Yeah.
it's like, what do you do to keep it on?
Yeah.
So that's gonna be an issue, or it may be an issue.
Yeah. Our actual testing, like the actual capturing of the signal,
Yeah.
it's under a minute. So the probability that there'll be excessive sweat in that time span, we decided would be very low.
Good. No, we have time for one more question.
Okay. So I did have a question with the device itself. So what age group are you guys going to be diagnosing?
We're basically targeting the geriatric population around those 16 older, because dysphagia is not normally seen in younger adults, 50 and down. You don't really see dysphagia. Dysphagia tends to develop after patients have suffered the most prevalent condition that happens with dysphagia is neurological conditions. If a patient has suffered a stroke, anything with the brain that affects muscle, contraction, that's usually like the group that we're targeting because dysphagia, like I said, doesn't really, you don't see it in younger adults. It's mostly gonna be in those age 65 and older. So our target population would be around 65 and older because they've usually been the ones that have the tendency to go through any type of neurological condition as those. Yeah.
I was also thinking of like the design and shape of the device. I was thinking of the shape of the device itself. Like how it would affect like different anatomies. So. No, I wasn't adding on to my question. I was just explaining where my question, like the root of my question came from. So I was thinking of like the anatomy of the patient. So it is a box and it's like a specific size. And then you guys, because I heard in the beginning of the presentation that you said that you would insert. So this is an opening and then the doctor would insert it and then they would lock it, correct? So how do I unlock it, or how do I, is this already prepared?
Yeah, that's already.
It comes.
Yeah, that comes already prepared. That's in more of like the manufacturing side, so it would come as is.
Okay.
Yeah.
Perfect. All right, thank you.
Okay, thank you very much, Team 2. I now call team number 3 to the stage. Team number 3. Shoulder brace for transcutaneous electrical nerve stimulation. The team members, Project Manager Franco Melis, Daniela Alayon, Braulio de Jesus, Ahmed Kasim. The project is sponsored by Beta Blue. The faculty mentor is Dr. Raj Pulagurtha, and the alumni mentor is Ms. Daniela Melendez. Let's give it up for team number 3. Team number 3.
Good morning, ladies and gentlemen, and welcome. Today, we're going to talk about the shoulder brace for transcutaneous nerve stimulation, or TENS. Our group is formed by Daniela Alayon, Braulio Jesus, Ahmed Kassem, and myself, Franco Melis. Our sponsor is Beta Blue, and you may ask yourself, why is this project important? I'll tell you why. Although brachial neuritis is a very rare disease, it does not discriminate on gender, race, age group, and it could basically attack anyone. It attacks the brachial nerve, causing a lot of pain and loss of muscle tonicity in the upper arm. Today, we're seeing more and more cases of this disease, as there seems to be a correlation between the metabolic syndrome or diabetes and brachial neuritis. Okay, but let's talk about our main focus, the patients. When a brachial neuritis patient undergoes transcutaneous electrical nerve stimulation, he or she does this around 3 times a day to reduce their pain. When they're setting up their electrodes in their arm, they engage in this trial and error methodology to get the placement correct. And after they set the electrodes, they don't even have a confirmation that the placement they chose for the electrodes is correct. When the placement is incorrect, the muscle tends to twitch. And treatment is not effective. Moreover, while researching about TENS devices, we found out that if you put the electrodes near the heart, aka where you're treating brachial neuritis for your left shoulder, you have the possibility of facing heart rhythm issues. But let's take a step back. What's the problem? The problem is that the market is lacking a device that facilitates electrode placement, that has electrode placement confirmation, and that has a way of alerting patients if arrhythmia or heart issues are occurring during treatment. We are solving this by developing a shoulder brace that provides an electrode placement grid that also has a surface electromyograph sensor and has a heart rate sensor to provide feedback and maximize treatment efficiency and safety. Brachial neuritis is a disease that causes pain or loss of function in the nerves that carry signals from the spinal cord and the brain to other parts of the body. Other risk factors besides diabetes include advanced age and alcohol use disorder. And future looks alarming for brachial neuritis patients right now, as there seems to be a prevalence in unhealthy diets nowadays, and therefore an increase in diabetes cases. The incidence of brachial neuritis is as high as 1 in 1,000 individuals, and currently there's no cure for the disease. The regions affected also include the shoulder, the hand, and the chest. And other treatment options include, but are not limited to, physical therapy, anti-inflammatory drugs, and our main focus, TENS devices. As most medical devices, our device needs to be compliant with the FDA, ISO, and ASTM standards. Assuming that 80% of brachial neuritis patients use TENS devices, and assuming that 40% of those patients integrate our device, we're estimating to obtain a revenue up to $466,000 in the first year. Now, I'm going to leave you with my teammate, who's going to talk about the current modalities.
Perfect. So the main way of treatment is, currently the standalone pens, and the main problem with this treatment is that the pens cannot provide user feedback, and that is where we come in. And that is where we come in with our that is where we come in with our thing here, yeah, pretty much Franco. So here we have a set that is made to make sure that we can so here we have a set that makes sure that we can provide accommodation. So in this set, we are making sure that we can provide accommodation to the different body sizes, and so here we can make sure that we can provide user feedback, and here is how we can make sure that the device is safe to use. Here we have a list of patents which have similar parts, which have similar parts that we have
so these pads have similar parts that we have. However, we are not. However, we are not infringing on these patents. Now I am going to leave you with. Now I'm going to leave you with Daniela.
Thank you, Ahmed. So the simulations we chose to do for this device were based around its day-to-day use. This came to be a stress tension test on both straps, where one end was fixed while the other one was pulled with 100 newtons force. This had a safety factor of 10 due to the fact that in average, a person suffering from muscle dystrophy has a pull strength of 10 newtons or around 2 pounds. So this simulation showed that our device can very well withstand this day-to-day use, and the brace is under no stress while this is going on. From here, we can move on to our design concepts. Both of these design concepts were considered, however, the top one could pose a safety risk as it would have to be applied around the neck and had no stability for the electrode placement. And the bottom one had some grid deformation due to the fact that it would have to be made of an elastic material in order to be secured around the upper arm. Our GUI app, however, both of these designs met all the market requirements. However, we moved forward with an MVP that was more empathetic design and was more user-friendly. Moving forward with our MVP, as you can see here, it features 2 straps that allow for adjustability to different body sizes, as well as stability during placement, and an electrode grid that allows the patient to replicate their placement from therapy to therapy, featuring numbers and letters. Our GUI app features a treatment section at the top, which interfaces with our heart rate sensor, and a calibration section at the bottom, which interfaces with our EMG sensor. Moving on to manufacturing, what was really important for us was consistency. We achieved this by printing out a template to not only print out the brace, but also to ensure that the grid placement will be the same from brace to brace. The brace is made of neoprene material, while the strap is made of spandex, neoprene, and Velcro material. Talking a little bit more about our sensors, here you can see a demo. Every section has instructions, and as we start off with calibration, a baseline is set. If during the baseline no sudden movements occur, as asked here, you can move on. While the muscle twitching light is red, it is important for the patient to change their electrode placement. Muscle twitching is a problem during treatment because if the muscle twitches, you are targeting the muscle and not the nerve, and pain persists. So once the placement of the electrodes is changed and the muscle twitching light is green for a prolonged period of time, you can move on to the treatment section. In order to manufacture the EMG sensor, we had to do some soldering of 3 wires. And as we move on to the treatment section, it's important to point out that patients will get information about their heartbeat throughout the therapy that they can provide to their healthcare providers after the fact if they so wish. During the treatment of heart rate, the heart rate is recorded every 15 seconds, and it's giving a gauge as well as a text box. And if the heart rate is over 100 beats per minute or under 60 beats per minute, as emulated here by hyperventilating, a lamp will turn on and